Section 1 Introduction. In this paper, we're diving into the world of software testing, a crucial step in the software development process that helps us find and fix bugs before new versions are released. One of the key ways we measure the effectiveness of this testing is through code coverage. This metric gives us an idea of how thoroughly our tests are examining the software, and it's so important that certain standards won't let software be deployed without reaching a specific level of code coverage. For instance, the Federal Aviation Administration, FAA, and the Automotive Safety Standard ISO 26262 both consider code coverage when certifying safety. To give you a clearer picture, let's say we have a method, or a piece of code, that we're testing. Code coverage measures how many of the statements in that method are actually being executed by the test. We can visualize this by marking the executed statements with a greater than, the missed or unexecuted statements with a, and any unreachable or dead code with a. From this, we can calculate various coverage metrics, like functional, statement, branch, and path coverage. However, calculating code coverage isn't a walk in the park. It involves instrumenting the code, running the test suite, and monitoring the code execution, which can be time-consuming and costly, especially for large software projects or when code coverage is calculated multiple times. Moreover, it's not possible to measure code coverage for a piece of code without having the entire program that contains it. This can be a problem when only a part of the code is available, like in a commit log or diff, or when only a part of the code is sent to a server for security or networking reasons. Recently, large language models, LLMs, have shown promising results in tasks related to code, like code generation and test generation. But we're still not sure how well these models truly understand code execution. To test this, we're introducing a new task called Code Coverage Prediction. This task evaluates how well LLMs can predict which lines of a method are executed based on a given test case. A model that can do this well could help us save time and resources in calculating code coverage, or even make it possible to calculate code coverage when it's normally not possible. In this paper, we're defining the Code Coverage Prediction task and evaluating how well LLMs can understand code execution by predicting which lines of a method are executed based on a given test case. To help with this, we've put together a dataset called CoverageEval, which contains methods annotated with code coverage information. This dataset was created by running tests and code from the Human Eval dataset, and we've made it available on GitHub for other researchers to use. We're also evaluating 4 of the top LLMs used for code-related tasks: OpenAI's GPT-4 and GPT 3.5, Google's Bard, and Anthropic's Claude. Our goal is to understand how well these models can predict code coverage, which could provide an alternative to traditional execution-based coverage measurement in certain situations. This could be useful when building and executing a program is too costly, when code coverage needs to be calculated multiple times, when only snippets of code are available, or when errors prevent a complete build. Plus, this task gives us a new way to measure code understanding and could be a valuable training objective. By training models to excel at this task, we believe we can improve their overall performance on code-related tasks. In summary, this paper introduces the Code Coverage Prediction task, evaluates 4 leading LLMs on this task, and presents a new dataset of coverage-annotated methods and test cases. We hope that our work will spur further research and advancements in code coverage prediction techniques. Section Summary. Code coverage is a widely used metric in software testing that measures the number of statements executed by a test case. However, computing code coverage can be expensive and challenging when only partial code is available. To address this, we propose a task called Code Coverage Prediction, which evaluates the ability of large language models, LLMs, to accurately determine which lines of code are executed based on a given test case. We also provide a curated dataset and evaluate the performance of 4 state-of-the-art LLMs on this task, offering insights into their code understanding capabilities and potential applications. Section 2 Background. Let's delve into the background of our topic. Code coverage is a way to measure how much of a software system is tested by a particular test suite. This is usually done by adding extra code into the software or its binaries to monitor its execution. This extra code keeps track of which parts of the software have been run by the test suite. However, adding this extra code can slow down the execution, especially for larger software programs. The most common way to measure code coverage is at the statement level. A statement is a single unit of code, like an assignment or an assertion, and usually corresponds to a single line of code. The coverage tells us whether a statement has been executed or not. We can then aggregate this data to see how much of function or program has been covered by the test suite. For example, if a test case executes 4 statements in a method, that's about 44% statement coverage for that method. We can also use statement coverage to calculate other coverage metrics. For example, we can use information about control structures, like if-else and case statements, to calculate branch coverage. This tells us how many logical branches in the program have been executed. In our example, only one branch is executed, while the other two are missed by the test case. For the rest of this paper, we'll focus on statement coverage, but keep in mind that other coverage metrics can be derived from it. Now, let's talk about the task of predicting code coverage. Suppose we have a method, which we'll call the focal method, made up of n statements. We also have a test case that runs this method. We can annotate the method with coverage information, marking each statement with a symbol to indicate whether it's been executed, missed, or is unreachable by the test case. This gives us a sequence of n coverage symbols. Our task is to predict this sequence of coverage symbols given the focal method and a test case. In other words, we want to predict which statements will be executed, missed, or unreachable. We can express this problem in terms of inputs and outputs. Inputs, focal method, m, test case, t outputs. The sequence of coverage annotated statements, or the sequence of coverage symbols. The output can be either the sequence of coverage annotated statements or the sequence of coverage symbols. If we have the sequence of coverage symbols, we can combine it with the original sequence of statements to get the coverage annotated sequence of statements. This is done by aligning the two sequences and concatenating each coverage symbol with its corresponding statement. For example, if we have a focal method m and a test case t, the model should predict either the coverage annotated sequence of statements or the sequence of coverage symbols. Section summary. Code coverage is a measure of how much a test suite exercises a software system, and it is commonly computed by inserting additional code into the program to monitor its execution. The most common coverage metric is statement coverage, which indicates whether each line of code has been executed or not. Other coverage criteria, such as branch coverage, can be derived from statement coverage information. The code coverage prediction task involves predicting the coverage annotated sequence of statements or the sequence of coverage symbols given a focal method and a test case. Section 3.1 Coverage Prediction for Pre-training. We suggest a new method for pre-training language learning models, LLMs, that are designed for code generation. This method involves predicting code coverage, a concept we introduce in this paper. Current pre-training tasks, like masked language modeling, MLM, help LLMs understand the syntax and semantics of code by analyzing large amounts of raw text that represent code. However, these tasks don't teach the models about code execution, which can't be learned from just reading the source code. Our proposed method addresses this gap. We recommend enriching the training data with extensive logs of code coverage. These logs are collected from continuous integration, continuous deployment, (CI/CD) pipelines. They provide valuable insights about code coverage from regression tests that are run during pull requests or commits. By exposing the models to these logs during pre-training, they can learn to link test cases and inputs with the specific lines of code that are executed. This method improves the model's understanding of how different parts of the code are used in various test scenarios. As a result, the models can gain a deeper understanding of the relationships between inputs, tests, and code execution. This leads to better code generation capabilities. Incorporating code coverage prediction into pre-training allows models to learn from real-world test scenarios. This helps them understand the subtleties of code execution in practical situations. This exposure to real-world scenarios should improve the model's ability to generate code that aligns with actual testing practices. Moreover, using code coverage prediction as a pre-training task creates opportunities for transfer learning. Models that have been pre-trained on code coverage prediction can be fine-tuned for downstream tasks. These tasks, such as bug detection or test case generation, require a good understanding of code execution. The model's existing knowledge of code coverage can provide a strong foundation for these related tasks, potentially improving their overall performance. Section summary. The proposed code coverage prediction task can be used as a pre-training task for language models focused on code generation. By augmenting the training data with coverage logs from CI/CD pipelines, the models can learn about code execution and associate test cases with specific lines of code. This pre-training approach enhances the model's understanding of code relationships and can improve their code generation capabilities, while also enabling transfer learning for tasks like bug detection or test case generation. Section 4 CoverageEval Dataset. In this paper, we introduce a new task of predicting code coverage and a dataset specifically designed for this task, which we call CoverageEval. We start by using the Human Eval dataset, which is a collection of handwritten problems and their code solutions. We run test cases from this dataset to gather code coverage information. We then parse the logs generated during these tests to extract relevant coverage annotations. This allows us to structure and export the dataset in a way that is easy for researchers and practitioners to use and evaluate. Our goal is to provide a standard benchmark for evaluating language models' ability to predict code coverage. The Human Eval dataset consists of 164 problems, each of which is a programming task that involves language comprehension, reasoning, algorithms, or simple mathematics. Each problem in the dataset includes a function signature, a problem description, a function body, and several unit tests. We extend this dataset to include coverage information, which we calculate using the function body and the corresponding unit tests. To create the CoverageEval dataset, we analyze the code coverage on the Human Eval dataset. Each code solution in the Human Eval dataset comes with a single test case, which includes multiple assertions designed to test the correctness of the code solution based on the problem's functional requirements. These assertions cover various inputs, scenarios, and code statements or branches. To make the dataset more complex, we split the single test case into multiple test cases, each containing a single assertion. This allows us to generate additional method test pairs and makes each data point more challenging. The original test case may cover most of the lines and branches in the method, but each individual assertion covers only a subset of them. By performing this split, we create a more diverse set of method test pairs within the dataset. Each individual test case invokes the method once and covers a subset of the statements and branches within the method. This allows us to evaluate the language model's ability to predict code coverage at a more detailed level, beyond the overall coverage of the method. It also adds complexity to the task, as predicting coverage for each assertion requires a deeper understanding of the code and its potential execution paths. Next, we run each test case individually using a tool called PyTest. During the execution, we also enable the computation of coverage using a tool called coverage.py. For each test case, we analyze the corresponding coverage report to extract the annotated coverage. The coverage report marks each source code line in the file with coverage information, specifying whether the statement has been executed or not. We automatically parse this report and extract the corresponding annotated coverage. At the end of this process, we obtain a dataset where each data point is formed by a triplet consisting of the method, the test case, and the annotated coverage. Section Summary. The paper introduces CoverageEval, a dataset designed for evaluating language model-based code coverage prediction. The dataset is curated by executing test cases from the Human Eval dataset and parsing the code coverage logs to extract relevant coverage annotations. By providing this standardized benchmark, researchers can explore and advance code understanding, leading to the development of more effective models. The Human Eval dataset consists of handwritten problems and their code solutions, which are extended to include coverage information. The coverage analysis involves splitting test cases into multiple asserts to generate a more diverse set of method test pairs and evaluate the ability to predict code coverage at a granular level. Section 4.3 Data Format. We've created a dataset called CoverageEval, which is based on the structure of the Human Eval dataset, but with added coverage information for each test. Each entry in this dataset corresponds to a unique problem and includes several fields. These are 1. Problem ID. This is a unique identifier for the problem. 2. Problem. This is the name of the method that was created to solve the problem. 3. Method. This includes the details of the method, such as the function signature, a docstring explaining the problem, and the function body. 4. Tests. This is a list of unit tests for the problem. Each test in the list has a unique ID and the test's code. We've also added coverage information for each test in two ways. 1. Coverage. This is the method's code, with each line marked with greater than, or, to indicate whether the code is executed, missed, or unreachable by the test. 2. Coverage sequence. This is a list that's as long as the number of lines in the method. Each value in the list is greater than, or, depending on the status of the corresponding line of code in the method. We've included a sample record from the CoverageEval dataset in the appendix. The dataset is publicly available on GitHub. We've also included a table that provides statistics for the dataset, such as the number of problems, code solutions, tests, and coverage symbols. Some problems have multiple solutions, which explains why the number of problems and solutions don't match. We've also considered the possibility of unreachable code in our dataset, even though there currently isn't any. Next, we evaluated 4 top language models, LLMs, for their ability to predict code coverage. These models are OpenAI's GPT-4 and GPT-3.5, Google's Bard, and Anthropic's Claude. GPT-3.5 and GPT-4 are large language models developed by OpenAI. They're transformer-style models that were initially trained to predict the next token in a document, and then fine-tuned using reinforcement learning from human feedback, RLHF. GPT-4 is an improvement over GPT 3.5 because it can accept both images and text as input and produce text as output. Bard is a conversational AI developed by Google. It's based on Lambda, which is a transformer-based language model trained on dialogue. Anthropic Claude is a 52 billion parameter LLM developed by Anthropic. It was pre-trained on a large text corpus and then fine-tuned using RL from AI feedback, RLAIF. This process involves using AI feedback guided by a small set of principles drawn from a constitution defined by humans. Section Summary. The Data Format section describes the structure of the CoverageEval dataset, which includes problem IDs, problem descriptions, methods, and unit tests. It also introduces the coverage information for each test, represented as annotated code or a coverage sequence. The Evaluating LLMs section presents the evaluation of 4 popular language models, LLMs, for the task of code coverage prediction, including GPT-4. GPT 3.5, Bard, and Claude, highlighting their features and training methods. Section 5.1 Experimental Design. In Section 5.1, we discuss our experimental design for evaluating language learning models, LLMs, on the task of predicting code coverage. Our goal was to test these models on complex coverage sequences, gradually providing them with more information and examples. Initially, we removed data points represented as D equals M, T, COV, M, T, where the coverage sequence was simple and consisted only of the symbol, greater than. These instances correspond to methods without branches or where the test case covers every statement in the main method. Even though these data points are part of the CoverageEval dataset, we decided not to include them in this particular evaluation. We've documented the subset of data points that only contain simple symbols in our online appendix. It's worth noting that there are no data points in the dataset that have a coverage sequence made up solely of, or, symbols. After this filtering process, we were left with 478 data points to evaluate the LLMs. We designed a prompt to evaluate the LLMs, which included several sections: a system natural language, NL, prompt, examples, and the main method, M, and test case, T. The system NL prompt provided a natural language description of the task to help the LLM understand it. We experimented with various prompts and descriptions and found that a system prompt mimicking a terminal environment, like a Python terminal, yielded the best results. In this prompt, we asked the LLM to generate the code coverage output based on a given test case and method. For OpenAI models, we included this prompt in the specific system prompt section, while for Bard and Claude, we incorporated it as the initial part of the prompt. To thoroughly evaluate the LLM's performance, we used different numbers of examples for the code coverage prediction task. We used zero-shot, one-shot, and multi-shot prompting approaches. This allowed us to study how the availability of examples affected the model's performance and their ability to generalize the task across various methods. When choosing examples to evaluate coverage on a specific method, M_I, we were careful to avoid data leakage and to encourage the LLMs to generalize their predictions to other methods. To do this, we randomly selected a data point, M_J, T, COV, M, T, where M_J is not equal to M_I when providing examples. Lastly, the prompt provided a main method, M, and a corresponding test case, T, for which we expected the model to predict the code coverage. We've included an example of the prompt we designed in the figure. We performed inference on all the LLMs with temperature and top set to 0, and generated one sample. Section Summary. In the experimental design, we filtered out trivial coverage sequences and evaluated the LLMs on non-trivial sequences. We used a system NL prompt, examples, and a focal method with a test case to evaluate the LLMs. We achieved favorable outcomes by using a system prompt that emulates a terminal environment. We conducted evaluations with different numbers of examples to assess the model's performance and their ability to generalize the task. To prevent data leakage, we selected examples from different methods. Section 5.2 Evaluation Metrics. In this section, we'll explain how we evaluate our method. We start with a method, a test case, and a sequence of coverage symbols. The model then predicts a sequence of coverage symbols. We use several metrics to assess how well our approach performs. First, we look at the perfect sequence match. This metric counts how often the predicted sequence exactly matches the target sequence, symbol by symbol. This would mean that the model has perfectly predicted the coverage for all statements and branches. Next, we consider statement correctness. This metric calculates the proportion of statements where the execution prediction is correct. In other words, it's the percentage of symbols in the predicted sequence that match the target sequence. We also measure branch correctness. This metric calculates the proportion of branch-specific statements where the execution prediction is correct. It only considers the symbols associated with branch statements and measures the percentage of these symbols in the predicted sequence that match the target sequence. We then present the performance of different language learning models, LLMs, on the code coverage prediction task. The table shows the percentage of predicted coverage sequences that match the actual coverage, match, the percentage of correct coverage symbols for all statements, STMT, and the percentage of correct coverage symbols for branch statements only, branch. We calculate these performance measures using zero-shot, one-shot, and multi-shot prompting. OpenAI GPT-4 performs best on this task, achieving an exact match of 24.75% with zero-shot prompting and improving to 30% with multi-shot prompting, where up to 6 examples are provided in the prompt. Other LLMs achieve low exact matches with zero-shot prompting, suggesting that these models may not have been exposed to coverage logs during their training. The second best model is Google Bard, with an exact sequence match of 21.5% with multi-shot prompting. When we look at the percentage of correct coverage statements, STMT, most models improve as more examples are included in the prompt. OpenAI GPT-4 scores best overall, with between 84% and 90% statement correctness. However, when we only consider statements involved in branches, like if-else, while, there's a significant drop in correct predictions. The best performing model, OpenAI GPT-4, accurately predicts only 22% of these symbols when one and multi-shot prompting is used. This subset of statements, which are closely linked to branches, presents a greater challenge because the LLM must understand the Boolean conditions that determine which branch is covered. Therefore, accurately predicting coverage symbols in this context requires the model to have a deep understanding of the conditional logic that guides program execution. Despite OpenAI GPT-4's strong performance on the code coverage prediction task, it's important to note that the model still fails to generate the correct coverage for more than 70% of the method test pairs in the CoverageEval dataset. This highlights that LLMs still have a long way to go in developing a deep understanding of code execution. We believe that to improve code generation results, these LLMs should gain a comprehensive understanding of code execution under different inputs and test cases. We assert that our dataset and proposed task can contribute to the advancement of LLMs towards this goal. Section Summary. In this section, the evaluation metrics for the proposed approach are described. These metrics include the perfect sequence match, which measures the accuracy of the predicted coverage sequence compared to the target sequence, the statement correctness, which measures the percentage of correctly predicted statements, and the branch correctness, which measures the percentage of correctly predicted branch-specific statements. The results show that OpenAI GPT-4 performs the best on the code coverage prediction task, achieving up to 30% exact match with multi-shot prompting, but still fails to generate the correct coverage for more than 70% of the method test pairs in the dataset, indicating the need for further improvement in understanding code execution. Section 7. Discussion and Applications. In this section, we'll discuss how language learning models, LLMs, trained for code coverage prediction can be a promising alternative to traditional methods of measuring code coverage in various situations. We'll explore several scenarios where this approach can be beneficial. 7.1. Large-scale software projects. For extensive software projects with millions of lines of code and many dependencies, the process of building and executing can be time-consuming and costly. In these situations, developers might want to examine the code coverage achieved by newly created tests without waiting for the lengthy build phase. By using LLMs trained for code coverage prediction, developers can estimate the coverage achieved by the new tests on existing methods without having to build the entire project or run the tests. This allows developers to quickly determine if more tests are needed to cover missed lines or branches in the methods, saving precious time and resources. 7.2. Limited access to code. Traditional methods of calculating code coverage require access to the complete source code of the codebase for instrumentation and execution. However, there are situations where only a partial view of the code is available, making it impossible to compute code coverage using traditional methods. In situations where limited access to code is a problem, the code coverage prediction approach can be used. For instance, when using an AI code generation service from an integrated development environment, IDE, developers may only send a partial view of the code to the server where the AI model is located. In this case, the server can use the proposed approach to predict the code coverage of the AI-generated test cases on the given method. This allows for an estimation of the code coverage without needing the entire codebase, addressing privacy concerns and network limitations. The predicted code coverage can then be used to make informed decisions, such as creating additional tests if coverage is inadequate or sending the generated tests to the user if coverage is satisfactory. Section Summary. LLMs trained on the code coverage prediction task can be a valuable alternative to traditional execution-based code coverage measurement in various scenarios. For large software projects with lengthy build processes, developers can use LLMs to predict the coverage obtained by new tests without waiting for the build phase, saving time and resources. Additionally, in cases where only a partial view of the code is available, such as when using an AI code generation service, the code coverage prediction approach can estimate code coverage without the need for the entire codebase, addressing privacy concerns and network limitations. Section 7.3 Live Coverage. In Section 7.3, we discuss live coverage. Live unit testing, a feature found in many integrated development environments, IDEs, provides developers with instant feedback on how changes in their code affect existing tests. It also points out if the new or altered code is covered by current tests. In this context, we can use the code coverage prediction method. Instead of actually running the test cases, we use an AI inference call to predict the coverage of the changed or newly introduced methods. This gives developers immediate feedback on code coverage without having to run the entire test suite. By using models based on lower-level manager, LLM, for predicting code coverage, developers can make the testing process more efficient. They can also get quick insights into the coverage of their code modifications. Section Summary. Live unit testing, integrated into various IDEs, allows developers to receive real-time feedback on the impact of code changes on existing tests and identifies whether newly added or modified code is covered by existing tests. By utilizing LLM-based models for code coverage prediction, developers can streamline the testing process and receive timely insights into the coverage of their code changes without executing the entire test suite.